today we're going to take a look at logarithmic functions. Is there anybody in this class that's never heard of the term logarithm or logs? Anybody never heard of that in their whole life? Yay! All right. Also, make sure test number 3 is going to be Wednesday. We come back from Thanksgiving break. And I was looking through your homeworks again last night, and I noticed that some people had problems with homeworks like 28, 29, some with the rational function homework. If you had trouble with that, 28, 29, please make an appointment to see me between now and before Wednesday the 12/3, so we can go over it and clarify any final questions you might have. Okay, so you can see me, and remember, I'm here when I'm lots of time other than my office hours, so you can always find a time with me, I'm sure. Katie? No. No? Yep. Hannah? I do. Let's see. Oh, in here somewhere. Let's see. Here we go. I don't think that has writing on it. Yeah, that should be it. We're on 34 today. Okay, anything else before we head into Logland? It's not Legoland, unfortunately. All right. Lincoln Logs, okay. All right, so last week, you recall, we were looking at some characteristics of exponential functions, and one of the questions was 1-to-1. And I said, why is this important? And we had to stop the lecture and have you all look it up or go back into your notes or go on your smartphones to find out why a function being 1-to-1 was important. And we all recall, through the help of some kind of resource, that if a function's 1-to-1, then that means its inverse is a function, which is really critical. So to start us off today, I put 5 important things we have to remember from in the our study of inverse functions. So we're going to go table by table, starting with Katie. You want to do A first, Katie? Katie Wilkins.
Only one-to-one function have inverses that are functions. We test if the graph is a function, if the graph of a function is 1-by-1 basic.
Right, so the horizontal line test tells us whether we're 1-to-1. If we woohoo, we have an inverse function. All right. B, Sean. Right, so we did this. This was our algebraic approach for finding the inverse function. We just switched x and y, and then we solved for y, and voila, we had our inverse function. Okay, C, Hannah. Right, and this was a really big discovery, especially for graphing a function in its inverse. We know that whatever the domain and range was of our original function, it got swapped for our inverse function, because the output of our function becomes the input. The output's the range, becomes the domain of our inverse function, and then it brings us right back to where we started, which is a value in our domain. That's what undoing each other means. It's that round trip idea we talked about. D, Isabel? Right, so we just swapped the input and output, the coordinate x and y coordinates. If we had a graph of a function and we were asked to graph its inverse, we know it reflects over this line y equals x, which goes straight through our origin, a straight line with slope 1. And finally, E, Evan? Right, very good. So anytime, no matter how funky they look, which they're going to start looking a little funky in about 20 minutes, if you compose a function and it's inverse. No matter which order you do it, you always come back to your original input, x. Okay, so these are the only types of functions that you can reverse the order of the composition and still come out with the same exact answer, x. All right, so I think hopefully by now we are familiar with the graph of f of x equals 2 to the x and g of x equals 1/2 to the x. One is an exponential growth function. Right here is a growth function. This is a decay. We know that both of these graphs pass the horizontal line test. If we pass any horizontal line through each of these graphs going from top to bottom or bottom to top, it only hits the graph in one and only one spot. So that tells us we have an inverse function, which is great. Great news for us. Why? Because if we want to solve one of these problems, in other words, if I say 2 to the x equals, and I just make up some weird number like this, 968, and I want to solve this for x, I know that when I solve equations, I perform these series of inverse operations. I have no idea how to get that x from being up in the sky in the x as a power, an exponent, down so that it's x equals something. I don't know how to do that. I don't know how to undo exponentiating with a base of 2. I have no idea. Well, I do, but we don't as of yet because we haven't gotten to that part in Math 107. So what I want to do is find some way of undoing this so that I get x equals some solution. Okay, and that's what we're going to learn how to do today. All right, so since an exponential function's 1 to 1, we know it must have an inverse function. So on this graph of 2 to the x, let's sketch the graph of the inverse function. So how do I do that? Does anybody have any recall of how I'm going to start to sketch this graph here of the inverse of f of x equals 2 to the x? How I sketch its inverse function, whatever that is? Yeah, Katie? Okay, so let's pick some points so pick some nice points, nice friendly points on the graph of f of x equals 2 to the x, and then we just swap the x and y coordinates, and then we perform a swap of the x's and y's. All right, so someone want to give me one friendly point on why f of x equals 2 to the x? 1, 2, and that's a really important point that Will pointed out because whatever the answer, whatever the partner is for 1, that tells us the base of our exponential function, 2. Because when x is 1, 2 to the 1 is 2, that tells us our base. That's a really critical point. So similarly, when we swap this 2, 1, that's now going to be on our inverse function. So I'm going to make all the points on my inverse function in blue. So I'm going to go to the right 2 and down, to the right 2 and down 1, and that's going to give us the very first point on our inverse function. Okay, notice we didn't put in the line y equals x. I'm going to do that. Oh, what did I do? Oh, 2, 1. Yeah, you got to watch me today. I'm not quite here. 2, 1. All right. All right, so there's 2, 1. That's our very first point. How about another point? Someone who didn't give me 1, 2. Who gave me 1, 2? Katie? Yeah. Someone else. Andy? 3, 8. Right. If I put 3 in for x and I do 2 to the third, I get 8. So let's go over and plot 3, 8. There I am at 3, 8. And so I know its corresponding point on my inverse function is what? 8, 3. Notice, again, here's my input 3. I perform something. I apply a function to it. I get 8. That's my output. I then take my output, put it into my inverse function. Voila, I'm right back to where I started. This is a wonderful thing about inverses. So now I go over to the right 8 and up 3. Here we go, 8, 3. Okay. Another important point, or a point that we can quickly get, and then we can start to maybe get a sketch. We need 2 or 3 more points, I think. Anybody else? 4, what? 4, 16, okay. And so then on our inverse function, it's 16.4. So I'm definitely getting a look at my end behavior now. I'm starting to see that this function is going like this. So now I've got to start seeing what happens to the left of 1 here. The left of 2, I mean. So I need to start getting a sense of the values to the left of 2. Okay, yeah, Caitlin? Okay, so 1 point on our original function is -1, and it would be 2 to the -1, which equals 1/2. That's right here. When x is -1, my output is 1/2. So Katie, on my inverse function, what would that look like? Over 1/2 and down -1. Okay, so I'm going to go to the right 1/2 and down -1. That looks like about right there. It's really hard to get these points exact, okay? What happens as I get closer and closer to 0? What's happening to this line, the graph of this, the line of this graph? What's it getting close to? 0. It's getting close to the line x equals 0, which is our vertical asymptote. Remember, on my original function, my horizontal asymptote was the x-axis. Now it reverses. It's now my vertical asymptote. So my horizontal asymptote was y equals 0. Now x equals 0 is my vertical asymptote. So this function is going to get really, really close to that y-axis. And what about our favorite point, the x-intercept? What's that going to be here? On my inverse function, what's my x-intercept going to be? 1, 0, because on my exponential function, all exponential functions go through 0, 1, unless they've been transformed in some way. So 0, 1 is the y-intercept on my exponential function, and therefore, when I swap my x and y values, voila, I get my x-intercept. So there we go. There's the sketch of my inverse function. And if you throw the line y equals 1 in here, it reflects across that line. Okay. There we go. Okay. So that's a sketch of the inverse function. We don't have a name for it yet, but we can see what it looks like. And we can see that every point has a mirror image over this line, another point on the other side of this line. Nice way to see this. I wonder if I can group this. Let me see. Oops, I got to get out of this. I think there's a way to group up here. Let me see. No. Oh, how do you group? How do you group? Because this is a pretty cool thing to see. Group, group, group. Let's group everything. It's not letting me group. Let's see, I'll try it one more minute. I'll take your time up here and see if I can group. Let's group. It's, oh, you know why? So I think I have to, maybe it won't let me do it because I can't edit this, right? Okay, but literally, folks, if you want to see that this is reflected over that line, take this picture and turn it like this. And then this looks like a y, like symmetry over the y-axis. If you tilt it this way, you can see that symmetry really nicely. All right, any questions on how you would find the inverse function or sketch it just from knowing the graph of our any exponential function? Are we all set here? This little review for inverse functions? Okay. All right, so to find the formula of an inverse function algebraically, as you know, we would start off with f of x equals 2 to the x, and we would put y in for f of x. We switch x and y, and then we solve for y. Uh-oh. We don't know mathematically how we solve this equation for y. We don't know how to do it because we need to undo the exponentiation 2 to the y. So I'm going to ask you to go with me here for 1 minute or maybe 2, and I'm going to tell you how we undo it. So we call the thing that undoes 2 to the y, log base 2 of y. That's going to be the inverse. That's going to be the inverse, okay, of 2 to the y. It's called log base 2 of y. All right. So let's see. So the equation for the function we sketched is f inverse of x equals log base 2 of x. So that means back here, this function we just graphed, this function is called a log function. And the equation for this function, knowing that it's the inverse of our 2 to the x function, is log base 2 of x. That's what it is, log base 2 of x. So this function, notice some things about this function. Our exponential function, remember when we were talking about earning a penny a day and doubling it for a month? It starts off really slow, the amount of money we make. And then after a certain number of days, our wage grew unbelievably fast. So exponential functions start out really slow and then quickly increase. Log functions start off quick, much quicker. They grow much quicker and then they slow down. So again, the idea between exponential and logs reverse. We also see here that the domain for our exponential function is 0 to infinity, right? 0 to infinity, not counting 0. And the range for a log function, every single number that's on this graph is to the left of 0. So they're always positive numbers as your input into your domain of your log function. We're going to get there. I should stop talking. All right. So it's this funny thing called log base 2 of x. So if you had something like this, 2 to the x equals 1028, for example, and I wanted to solve this, to undo it, I literally have to write in log base 2 of whatever it is I'm looking at on each side. So I would do this, log base 2 of 2 to the x, because that log base 2, the stuff in red, is the inverse. It's just like when you're solving an equation and you have plus 2 on a side of the equation, you subtract 2 from both sides, because that's the inverse of adding 2. Well, this is the inverse of 2 to the x. It's called log base 2. So you would literally do that on both sides of the equation. Okay. Now, right now, you don't know how this becomes the next thing I'm going to show you. This thing becomes x, which is what you want to solve for, x. And log base 2 of 1028, does anybody know what that is? 2 to what power is 1028? 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th. So this tells you the answer is 7. And in just a few minutes, you're going to learn how to go from this point down to this point. Okay, you really are. But I wanted you to see how you apply the inverse function to an equation like 2 to the x equals 1028. You literally write it in on both sides, okay, to solve the equation. All right. You're not going to know this yet. But if you check, Isabel, 2 to the 7th is 1028. Okay? 2 to the 7th. If you multiply, if you put that in your calculator, 2 to the 7th. Oh, wow, I'm making myself 1028. Thank you. All right, 1028. Oh, okay. So it's 7. Thank you very much. I'm glad you're following along here. 128. Right. There's no way 2 to the 7th can be in the thousands. Come on, Kavanaugh. All right. So what does this all mean? What this all means is if you look back at this graph, we can now start talking about some of the characteristics of this graph right here. We know that the input into our log function has to be positive. Why? Because the output of my exponential function is positive. So what you need to start to understand is that these two statements right here are equivalent to each other. So you will develop Notice I'm being very positive here. You will develop the ability to go from one form to the other. You'll be able to go from exponential form to log form and log form to exponential form. Okay, you'll have lots of practice going between these two forms. Those two equations are exactly the same. They're exactly the same. And so what do you notice about these equations? This first equation, this log equation here, says that your base of your log is b. Notice in your exponential equation, the base of your exponential is exactly the same. So whatever you see here for the base in your log is the base for your exponential. Notice the output of your log. The output here is y. That's your exponent here. So are you telling me that all this fancy notation here is just an exponent? And I'm saying yes. If you can sort of in your mind say all that a log is, all this thing is an exponent. It's that exponent right there. So if I was doing this exponential function and I put some number in for my exponent, out would pop the answer. That answer, the output, is now the input into my log. The answer to a log is an exponent. It's the exponent of its inverse function, the exponential function. So it's a lot of blah, 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 blah until we just say it. So let's do it. Okay, let's just do the math. So here's a log equation. Okay, I want to turn this log equation and rewrite it into an equivalent exponential form. Okay, so one of the things I do, especially if I'm new to logs, is I put this little box around my log and I just say, that is a fancy way of saying my exponent is 2. My exponent is 2. What's the base of my exponent? Can anybody tell me the base of my exponent? 3. It's the same as the base in your log, which is this little baby subscript here. So I write 3. I say, what power do I raise it to? It's whatever this log is equal to. That's my power, my exponent. A log is the same as my exponent. And now the output for 3 squared, 9. Notice this is the output for one function, and it was the input in my log function. Outputs and inputs just swap places with inverse functions. Now, another way to see this that's really kind of cool is if you write log base 3 of 9 and you represent 9 as a power of 3, because that's your base. How would you represent 9 as a power of 3? Replace 9 as a power of 3. What would it be? How can I represent 9 right here? I'm going to replace it as a power of 3. 3 times 3, which is what? 3 squared. So I can replace 9 with 3 squared. So what is this asking me? This says, what number do I raise 3 to get 3 squared? What's my answer? What number do I raise 3 to? What power do I raise 3 to get 3 to the second power? It's so easy, it's hard. What number do I raise 3 to get 3 to the second power? 2. So all you have to do is lift off, lift off, lift off. We have lift off, Houston. Just lift off the power. So in other words, when I look at this, I automatically see 2 because I see 9 as 3 squared. And log base 3 of 3 squared, these bases are the same. So I'm just putting my exponential function into my log function. This is a composition here. Here's my exponential function. Here's my inverse. When I put them together, what do I come back with? My original input, which is my exponent. All right. So that's just one way you can quickly get the answer without even having to go over here to this exponential form. I'm going to show you both as we go through these. And again, it takes a while, and I have had a lot of experience and practice, so you may not be as quick as I am, but it will come with some practice. Okay, what about the next one? Can we write this in exponential form? Okay, what's the base? What's the exponent? And what's the output in my exponential form? So this is a log form, and let's put it in exponential form. Can someone help me with this? The base is 8, right. Perfect. All right.
Exponent would be negative.
Yep, because the answer to a log is just an exponent. So this is my exponent. And what's 8 to the negative 1 give me? 1/8, which is, again, this output is the input to the log. Right. The other way to do it, if we want to make it look like we just did here, can we rewrite this log base 8 of 1/8 so that we can write 1/8 as a power, 8 to some power? Certainly, we can write it as 8 to the negative 1. So notice, here's my exponential piece, and here's my log piece. When I compose them, I come right back, I lift off this exponent, and I get negative 1. That's all I do. Okay, so that's going from log form to exponent form. Let's try it the other way. Let's see if we can go from exponent form to log form. So here's a simple exponential equivalency. 2 to the third equals 8. So how do I put that same statement in log form? How do I write the same statement in log form? Other than Andy and Will, and who else has helped me? Caitlin. Someone else want to help me with this? I'd write log first, absolutely. Yep. Go ahead, Dylan. Yep. I put a little 2 for my base. Yep. What's the answer to my log going to be the same as? What's a log equal to? A log is an exponent. So what's my exponent here? In my first sentence, my exponent is 3. So that's the answer to my log. Guess what? There's only one other place for the 8. That's my input. All right, so log base 2 of 8 is 3. How can you see that? Represent 8 as 2 to a power. Voila, there's my composition of my exponential form and my log form. I lift off my exponent. There we go, 3. 2 to the third equals 2 to the third. Okay, what about the next one? Anybody want to give that tricky one a little try here? 6 to the negative 2 equals 1 over 36. Yep, Patrick? Log base 6, so I've taken care of the 6, yep. Is my input into my log function. And what's my output? Negative 2 the exponent, right. So log is simply a fancy way of writing an exponent. And again, if you write 1 over 36 as 6 to a power, you see it's 6 to the negative 2. So I lift off my exponent, and there's my answer. There it is, negative 2, no matter which way I do it. Okay. So now let's evaluate each of these logarithms based on what we just found. Can we first, without putting it into exponential form, can you represent the input here? Here's the input into my log function. Can you represent it as 10 to some power and just lift off the power to get the answer? Can you represent 100 as 10 to some power? What is it? 10 squared. So to get my answer, I lift off my exponent. Our bases are the same. Boom, there's my answer. Log base 10 of 100 is 2. How do I check it? I check it with doing the inverse. 10 to the second equals 100. Voila, I know I'm correct. You try the next two at your seats and let me know if you have any questions. I'll be glad to help you out. Put up your flag at each table when you've completed B and C, and you're all. Log base 5 of 1/125th. What did we get for that? What did we get? Negative what? Negative 3. And how do you check it? 5, we keep the base the same. The log is the exponent to the negative 3 equals 1 over 5 cubed, which equals 1 over 5 times 5 times 5, which is 125. The other way to look at it is, can I write 1/125th as 5 to some power? And I can. It's 5 to the negative 3. And now I just lift off my exponent for my answer. Because all I've done here is I've composed my two functions. Here's my exponential function. That is now the input into my log function. These are inverses of each other, so my output is exactly the same as where I started at negative 3, my exponent. This one says 36 raised to what power is 6? Now, if you can't figure it out because you forgot that it's the square root, you could have done this. 36 is 6 squared. How the heck is 6 to the second going to equal 6 to the first? Well, what do I do to both sides to get 6 to the second to equal, just come out to be a 6? I raise it to the 1/2 power, because when I multiply 2 times 1/2, I get 6 to the first, and whatever I do to one side, I have to do to the other. So this is 6. What did I do here? I'm really messing up today. Yeah, it's 6 squared. Oh, I want to come out, right. I want it to come out to be 6 to the first. So I have to take the 1/2 power here, and that's equal to 6. So I have to take the square root of 36 in order to get 6. I was just trying to show you another way in case you forgot. All right, so question mark here is 1/2. This 36 to the 1/2 power says find the positive square root. That's what the rational exponent 1/2 says. It's 6. All right. So these basic, I'm a little off today, folks, because I got bad news over the weekend. I found out my nephew died, and then today I found out one of our adjunct teachers died over the weekend. So I'm a little bit in shock here today. So that's why my usual, I make mistakes all the time, but I'm a little off today, so I apologize. So keep on top of me today. All right, so these are basic log properties. Now remember, if you have basic log properties, they must have some relationship to basic what properties? Exponential properties, right? So let's look at some exponential properties. If I have b to the 0, what do I get for my answer, assuming b is not 0? B to the 0, what's that going to give me? 1, right? So if I put this in log form, what would this look like in log form? In log form, I'm looking at log base b of 1 is my exponent, 0, because we're just switching places. Here it's the input 0 and my output is 1. Now my output becomes my input into my log function, and my output is the original exponent, 0. So when you see log of any base and the answer is 1, boom. Just like when you say b to the 0 is 1, you say log base b of 1 is 0. And you can check it by putting it into exponential form. B to the 0 is 1, you're happy. Okay. Now, what happens when I take b and I raise it to the first power? What do I get back again? It's boring. What do I get back? B. So when I take that and I write it in log form, I say log base b of b gives me a 1 back, because b to the first gives me b. So when you have the same exact base for both your log and your exponential, you just literally look at the exponent that's sitting there with the b, and you say, oh, I lift off my exponent. In this case, it's just b to the first. So I lift it off and I get 1. All right, folks, if f of x equals b to the x, and f inverse of x equals log base b of x, then what am I doing here? Here I have two functions going. I have my log, which is in red, my log function, and my exponential function, which is going to be in green. Oh, that's supposed to be green. There we go. So I'm putting into my log function. My log function is my outside function. That's my inverse function. I'm putting into that, excuse me, let me make that red. I'm putting into my log function, which is the inverse function. What am I putting in there? I'm putting in my exponential function. So I'm composing two inverse functions. I'm putting b to the x into my log function. I have to come back to what when I compose inverses? What do I come back to? What's my answer? X. Notice if I erase all this stuff back here, you have the base b and you have b to the f, x, you simply lift off your exponent. There you go. That's a little easier to see than the next one. The next one, my outside function is my exponential function. It's b to the x. Here's b to something right here, b to something. That's my exponential function. Now it's on the outside. My input into my exponential function is my log function. So where I have an exponent, I put in my log. I'm still composing a function in its inverse. So what's my answer going to be here? If I compose a function with its inverse. What's my original input inside here? What's the original input? What's going into my log base b function? You don't know what the input is here from looking at this? X. So I'm back to X. Okay. Make this into something with numbers, and it's almost ridiculous to say. It's one of those things that's hard to say, but when you actually see it, it's like it almost feels redundant. Again, it's a little easier to see C because you can see in C, you see your exponential function going into your log. Here, your log function is going into your exponential. You're composing them. Remember composition of functions? Let's change all these b's and x's to numbers. Let's do something we're familiar with, like let's say base 10, b is 10, and I'm going to say log base 10 of 1,000 up here. So look at that. So what this says here, if I just look at my exponent, this is what my exponent is asking me. Log base 10 of 1,000. It really sounds silly to say. This exponent right here says, what number do I have to raise 10 to get 1,000? What is that number? What number do I raise 10 to get 1,000? 10 to the 10 is 1,000? 10 to the 100 is 1,000? 10 to the third is 1,000, right? So here it's asking you what number you have to raise the base 10 to get this input. This is your original input, 1,000. Your answer is 3. So then you replace that with 3. And what are you going to get back? Of course, you're going to get back that number, 1,000, where you started, what you started with. So it's just a real funky way, and it's hard to say. It's asking you, the answer you get from this exponent is the power you raise this to get that same thing right there, 1,000. You're coming right back to where you started because you're composing a function with its inverse function. It looks really strange, but anytime you see something of this form where your bases are the same, your answer is X. Similarly over here, when your log function's on the outside, and you have base b and your exponential function is your input, and that's the same base, your answer is x, whatever it is. You just lift off the exponent there. Okay, so similarly here, if you rewrote this, just not to make things more confusing, but if you rewrote this as 10 to the third, the answer to all this baloney here uses this idea. It's just 3, 10 to the third equals 10 to the third. All right. It takes a little while, especially these last two properties, but you'll use them often, so I think you'll finally get the hang of them. Please make sure you spend some time with these 4 properties because you'll be using them quite a bit. Okay, well, the good news is we have 2 log buttons on our calculators. Did I put a calculator at each table? No, I thought I had them out. Okay. Okay, so could you guys just pass one across to each table, one calculator? So if you don't have a graphing calculator, you can each take turns using this graphing calculator I'm passing around. Okay, so whenever we have a log that's base 10, it's what we call the common log. It's so common, we don't even bother writing in 10 as the base. So if you see log and then a number here, you can assume the base is 10. Anytime you see log of x, that tells you the base is 10. 10 to some number gives you x back again. So if you're trying to evaluate log base 10 of a, is that your quiz? Could you hand it in, please? Oh, okay. Can I have your quiz, please? Thank you. Thank you. So if you're trying to figure out log of 1,000, this tells you it's 10. Your base is 10. So we know we don't even need a calculator, hopefully, to do this, because you know this is true. And if you put in a little 10, you're saying, what do I raise 10 to get 10 to the third? 3. I lift off my exponent. But if you wanted to do this on your calculator, you hit this big log button here, log of 1,000 is 3. Okay. Now, if you have a decimal, a number between 0 and 1, you know your exponent. Think of our log function we just graphed. If we're between 0 and 1, let's go way back to where we were at the beginning of class here. Oops, not that far back. This is faster than I thought. Okay. When we were graphing our log function, right here, the blue, if you're a number between, if your input is a number between 0 and 1, like 0.01 or 0.001, you have to have an output that's negative. So if we're asking for the log of the number 1/100th, that's what that decimal represents, log of 1/100th. 1/100th is clearly between 0 and 1 in our log function in the domain. The output is below the x-axis. It has to be a negative number. So in your mind, hopefully you can say to yourself, 1/100th is the same thing as 10 to the negative 2. So if I take log base 10 of 10 to the negative 2, I just lift off my exponent, negative 2. Okay, now this one I mentioned when we were studying the number e last Friday, I think it was, that it was called the natural base. And so if we take the log base e, we replace that notation, log base e, with these 2 letters, ln, the log de natural. I don't know. I made that up. That sounds like it makes sense, right? French, because the adjective always comes after if you know French a little bit. So ln, natural log. So when you see ln, it's log base e. That's what it means. So here, this is really saying log base e of e to the third. What's my answer got to be here when I compose those 2 together? 3. You just lift off the exponent. And if you throw that into your calculator, natural log of e to the third here. So let's do that. I get this ln button. I hit it and I say e. Here's my e right here, e to the x. So I have to hit second ln and I put my third power in there. And I hit enter and there's your answer, 3. Okay. So these first 3, in fact, this fourth one you can do without a calculator. It's this last one you need a calculator for. So what about this one? Can anybody tell me what my answer is to this one without a calculator? If you haven't done it with a calculator, can you tell me how you can figure it out without a calculator, like with something called your brain? Anybody figure it out with your brain versus a calculator? Nobody? It is -2. How'd you get that, Drew? Yep, and then you just lift off your exponent. Yep. Log base c is the same as natural log e to the -2. These bases are the same. You just lift off your power, -2. So the only thing we can't figure out with our brain, well, maybe some people can, I can't, is e to what power is 5? Because that's what this is asking. E to what power is has the answer 5? So in order to do that, you really do need your calculator. Natural log of 5. And there's your answer. So all we can do is approximate it with little squiggles, say 1.609 perhaps, 1.609. Okay? So there we go, 1.609. Any questions on how to use your calculator if you have one? Yeah, Katie?
What if you had, I mean, I guess you could figure it out, but base up.
If you want to have a base other than 10, you have to come to class on Wednesday. Okay? Yes. Yeah. Anytime you see ln, that's the natural log. Okay? That means your base is e. Any other questions? Like I know a lot of this is either new or you only had a little bit of this before in maybe high school or something. Any other questions? Okay, unfortunately, the next part of my Smart Notebook didn't graph the picture very well. But this, you have the picture really nicely right here in your notes. So I'm going to take all this off to the side. Let's take a look at all this stuff for each of our graphs here. So I just called up the PDF file so I can have the same picture that you do at your seats, okay? So here's our exponential function b to the x when b is bigger than 1, that's a growth function. Here's our exponential function when b is between 0 and 1, that's our decay function. And then if we reflect each of those functions over the line y equals x, we get our logarithmic function, which is its exponent. Its inverse. So let's see what we notice about these things. If we have an exponential function, we know that our horizontal asymptote is the x-axis right here. We know we go through 0, 1. And so conversely, we go through 1, 0 for our log function. Okay, our log function is represented by log base b of x. If we have b to the x as our exponential function, the log function is log base b of x. All right, the horizontal asymptote for our exponential function now gets changed into a vertical asymptote for our log function. We had the function, the equation y equals 0 here. Now our vertical asymptote is x equals 0. Because remember, x and y change places. Similarly, with our exponential decay function, we go through 0, 1. We still go through 1, 0 with our log function. Our domain is all real numbers. Our range is all real numbers. Okay? And then I think everything else is pretty much the same as it was here with your horizontal asymptote x equals 0 becoming y equals 0 for your vertical asymptotes. So these act just like they acted before when we were just studying regular old inverses that were polynomials. Same exact idea. So let's take a look at a couple more problems and then we can go into your group activity for today. Am I missing anything here? Nope, we're going right to 14. Okay, so here's 14. Okay, we've already seen this several times. This is now A log function, again, if I gave you this on your final exam and said, give me the equation for that graph, hopefully you recognize that it's a log function. Again, remember these log functions, they grow very quickly and then their growth starts to slow down. Okay, but they continue to grow. It just doesn't increase very rapidly. Okay, now, again, you look for those key points, just like you had key points on your exponential function. On this log function, you go through 1, 0. Its corresponding really interesting point on the exponential function was 0, 1. And all that tells you is that it's a log function. It hasn't been stretched or shrunk or moved up and down the y-axis or right and left on the x-axis. It's one of your basic log functions when it goes through 1, 0. To find the base of the log, remember, to find the base of your exponential function, you went over to 1 and then up to whatever the point was on the graph to find the base of your exponential. So reverse that. Now we have to say, where does my log function cross y equals 1? It crosses y equals 1 at 2. So that tells me the base of my log. Because 1, 2 told me the base of my exponential, and all I have to do is switch it. So this line, y equals 1, going right through your log function, is going to be really important for you to say this function is log base 2 of x equals some output. So when you're trying to find your log function, you find, first of all, does it go through 1, 0? Yes, good, great. Then I don't have to worry about transforming that. Then I find the x value for when my y value is 1, and that tells me the base. Right. So with all your knowledge of exponential functions, I've done 2 transformations here. I'd like you to take 5 or 10 minutes and see if you can sketch, just sketch, knowing what happens with how these functions are being transformed. Try to do a quick sketch onto these 2 graphs here of these 2 new functions. Okay. And then we'll continue on at the end if we have a little time. So let's take a look at the first function. Oh, I don't think I've ever tried putting a log in here. We won't use any kind of graphing utility. So what's going on here? Our original function, our parent function is log 2 of x. So let's call f of x log base 2 of x, which is what we're looking at right here, log base 2 of x. That's this function. Notice our vertical asymptote is our y-axis. Notice we go through 1, 0, 1, 2, 4, 2, 8, 3. Those are some of our famous points. So we have 1, 0, we have 2, 1, we have 4, 2, we have 8, 3, and going the other way, if I'm at 1/2, I'm at -1, 1/4, I'm at -2, okay? So what does this transformation say to do to my original log function? What does it tell me to do? Shift left 3 units, right? So this tells me to shift to the left 3 units. So what that means is if I have some points on my original graph, I subtract 3 from all my x values. So that's what I'm going to do. I'm going to take my x value and take 3 away from it. And then I'll have some nice points on my new transform graph. So if I subtract 3 from 1 here, what do I get? 1 take away 3, -2, 0. So let's put these in red. So -2, 0. What's 2, 1 become? Notice all my y values are staying exactly the same. It's just my input that's been messed with. So what does 2, 1 become now if I'm subtracting 3 from all my x values? Someone just said it. Yep, -1, 1. So we go -1, 1. And then 4, 2 becomes 4 take away 3. 1, 2. Okay, 1, 2. And then 8, 8, 3 becomes 5, 3, 5, 3. So this is how transform functions grow. And now the big idea here is if my vertical asymptote was this line x equals 0, this whole thing moves to the left 3 units. So right through -3, boom, 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 I have my new vertical asymptote. And so this function comes down and hugs that all the way down to -infinity. Okay? So there's the graph of log base 2 of x plus 3. What's happening in my next function? How is my original function log base 2 of x being transformed? What's happening here? Vertical or a vertical reflection or a horizontal reflection? Horizontal, you're saying horizontal because it goes over the x-axis? Well, that is really a vertical reflection, right? Because you're affecting your output, right? You're taking the opposite of all your y values. It's a little strange, right? But you're reflecting it over the x-axis, which is changing all your y values to its opposite. Okay, so that means all of these y values are going to change. So if we stick with these same points, 1, 0, 2, 1, 4, 2, 8, 3, and we just flip the y values, well, 1, 0 stays the same on both. 2, 1 becomes 2, -1. 4, 2 becomes 4, -2. 8, 3 becomes 8, -3. And let's see, what else did we have? We had 1/2 -1 becomes 1/2 1. So 1/2 1. 1/4 -2 becomes 1/4 2. So I start climbing the ladder now. So this thing hugs the y-axis this way and comes down like this. So that's the reflection over the x-axis. Now some of you I know have the ability to flip this and flip that up and see it. I mean, some people have that visual acuity. I have to do it this way with the points. All right, the last thing we have to cover for today is the domain. So what's the domain of this function, x take away 3? Well, first of all, what's the domain of any regular log function, regardless of what its base is? So here's a picture of a regular old log function. What's the domain here? 0 to infinity, right? Remember, we can never put a negative number in for our log. So, oops, it's parentheses 0 to infinity. So that means our input always has to be greater than 0. So now to find this, well, one thing you could do is just to say to yourself, how has this been transformed? How has log base 4 of x been transformed? It just says I've shifted to the right 3 units. So now my new function is going to look like this. So my domain for my new function, the domain is 3, infinity. But let's suppose you didn't think about the graph. How would you do it? You take your input and you say, my input has to be greater than 0. You just solve the inequality. X minus 3 is greater than 0. You add 3 to both sides and you get x must be greater than 3. So your domain is 3, infinity. Okay, so that's it for today. I'll see you on Wednesday. I should have your quizzes back to you by Wednesday.